In this talk, I'm going to talk about sharpness-aware low-dose CT denoising using conditional generative adversarial network. I have no relevant conflicts of interest to disclose. In the very beginning, I would like to give you a brief review of the CT denoising methods. They can be divided into three groups based on the input data it manipulates. Sinogram domain processing operates on the raw projection data, which is also a 2D signal, so most of the image processing methods can be directly applied here. But this data most of the time are hard to have access to. Image domain processing method operates directly on the reconstructed image, and most of the methods are originally designed for natural image denoising. For example, the one based on non-local similarity and the one based on compressive sensing. BM3D and KSVD are two state-of-the-art traditional methods in the pre-deep learning era. With the resurgence of deep learning, we can use a neural network to minimize the mean square error between a low-dose CT and the conventional full-dose CT. But all the methods suffer from over-smoothness of the surface texture. The third group is the iterative reconstruction method. It iterates back and forth between the sinogram domain and the image domain by incorporating different physical models. For example, Acer incorporates the photon counting statistics, but was found to be only effective for dose reduction of 40 to 60%. VIO, on the other hand, has more complex models built in and produce a much sharper image, but produces a different surface texture than filtered back projection. Our work falls into the deep learning group, and we use a adversarial network trying to mitigate the over-smoothness problem. The objective is to evaluate the potential of conditional generative adversarial network on low-dose CT denoising. We refer our proposed method as SAGAN, the sharpness-aware conditional GAN, because besides the traditional setup of GAN, the generator G and the discriminator D, we employ another network S that explicitly measures the sharpness of the image. Generator G is the one responsible for denoising, and the discriminator D tries to discriminate the denoised CT and the conventional CT, and both networks is conditional on the low-dose CT. The denoised CT has to fulfill these three criteria. The first is look similar to the conventional CT, like sharing the same content. The second is having the same sharpness as the conventional CT. And the third one is the denoised CT has to pass the test of a discriminator. We use two datasets to evaluate the efficacy of the proposed SAGAN method. The first one is a piglet dataset we built by ourselves. So we scanned the deceased piglet under 100 kV and using 0.625 mm slice thickness, and was scanned from head to pelvis to cover a wide range of anatomic regions. We performed 5 series of scans with different tube currents to obtain images with different noise levels. The conventional full-dose CT has a tube current of 300 milliamps, and the tube current was subsequently decreased to 50%, 25%, 10%, and 5%. The lowest dose level has an effective dose of 0.7 millisievert. The 4 lower dose CT are combined together by using the conventional full-dose CT as the ground truth. This setup is trying to evaluate the generality of the single SAGAN on a variety of doses. The second dataset is a CATFAN 600, and we use it to evaluate the spatial resolution of the denoised CT image. This phantom was scanned at 120 kV using 0.625 mm slice thickness, and the conventional full-dose CT has a 300 milliamp tube current, and the low-dose CT has a 10 milliamp tube current. We use PSNR and SIM to compare the difference between the denoised CT and the conventional full-dose CT. And we also use the mean standard deviation of 42 hand-selected homogeneous regions as a direct measure of the noise level. We choose a couple baseline methods for comparison. The first is a filtered back projection, and the second is Acer and VIO, which are two commercial iterative reconstruction methods available to us. And the third group is BM3D and KSVD, which are two traditional state-of-the-art image denoising methods. Now let's have a look at some results. On this page, I'm showing you the Pearson R and SIM. With the higher value, the better. The x-axis from left to right represents the increase of dose level. SIGINT, as denoted by the orange line, gets the highest performance in the two lower doses, and it was only surpassed by BM3D and KSVD. Actually, their highest number was achieved by a sacrifice of image sharpness and image details. An average SIM of 0.95 of a SIGINT denoise result in the lowest dose level is almost equivalent to the image quality of the second highest dose image, which has an effective dose of 3.5 millisievert. On this slide, I'm showing you the mean standard deviation of 42 hand-selected homogeneous regions. With the lower value, the better. The red horizontal dashed line shows the noise level of the conventional photo CT. You can see that the SIGINT result, as denoted by the orange line, is very close to the reference line, because SIGINT has learned the noise statistics of the conventional photo CT. BM3D and KSVD here achieve the lowest value, only because they have smoothing out the image surface details. This page gives you some visual examples of a piglet dataset. I crop some patches so that you can have a better examination. The first column shows the low-dose CT, and the second column shows the conventional photo CT. SIGINT results was shown on the third column, and VO results was shown on the first column. You can see that SIGINT results got a very similar texture as the conventional dose CT, while on the other hand, the VO produced a very crisp surface texture. This is the result of the spatial resolution module. On the image, we have some patterns of line pairs of different spaces, ranging from 1 line pair per centimeter to 21 line pair per centimeter. As shown in the zoomed region, we can see almost equally well the line pairs on the SIGINT denoise results as on the low-dose CT. In conclusion, SIGINT is very promising for low-dose CT denoising, based on our experiments. It runs very fast in testing stage, which only requires less than a second to process a single CT image. The denoised CT resembles the texture of the high-dose CT and has very limited resolution loss. It also achieved a very high noise reduction factor, which is 1.93 in our case. If you have any comments or questions, please send email to the following address. Thank you so much.